Hi, this is Mr. Merrill, and we're going to take a look at an example where we're asked to mathematically combine vectors in a certain way. We should be pretty confident graphically, but it's a little more complicated process if we want an exact answer at the end. So we're given two vectors, A and B, and those are shown. And then we're asked about a vector C. We aren't shown what vector C looks like, but we're told C is made by taking negative 1/4 of A plus B. And then we're asked to report C given its magnitude and direction. So this whole process is a rather long example, so feel free to skip ahead if you're already confident in a certain part. So the first thing you need to do is get everything in component form. We can't do anything with the magnitudes. Vectors can only be added, subtracted, multiplied, that type of thing, if we're looking at their components. So to do so, let's first sketch out what those components look like. And again, no thought should go into this. If the vector goes down and to the left, the components go down and to the left. If a vector goes down and to the right, the components go down and to the right. There's no complicated process there. It's just realizing what the vector's doing. And then once we have those components sketched out, we can actually solve for their lengths using right triangle trigonometry. And again, we're back to this relationship. That's a good thing to hold on to. What this allows us to do is look at these components like sides of a right triangle. So we can find for the lengths of those triangles, the magnitudes of those components, using these sines and cosine functions. So those will give you positive numbers in the calculator, always positive. But we have to think whether there should be a negative there or not. And in the case of A, both the x component is negative because the x component goes to the left, and the y component is negative because the y component goes down. Here we see in B, when I calculated it, the x component was positive because B's x component goes to the right. So the calculator will be able to tell us the size of those components, or the length of the triangle I make when I stack those components next to each other. It does not, however, tell me the sign of those components. That's something I have to think about. So once you have the components form of A and B, now we can begin to think about the actual manipulation to get C. So we're told C is related to A and B in this way. And every time we're given one of these relationships, what we're really being given is two equations. We're being given the fact that the x components must add and subtract in this way, and also the y components must add and subtract in this way. So I took this relationship and I come up with these two separate equations. So since I solved what the components of A and B are, I can just substitute in here. So you see, when I see an A sub x, I just look, okay, what's the component A sub x, and I plug it in there. Same thing with all the others. And then simply using your calculator to add or subtract or multiply, all that stuff. And you come up with the x component of C and the y component of C. So now we can write C in component form, and that's what we have here. And you'd think we'd be done, but not quite, because the question asks us to report C in magnitude and direction. Right now we just have C in component form. So what we do is we start out by sketching the components. So here's the y component, we can add that to the x component, and then I can draw the vector C, and it looks something like that. So now that I see this right triangle, I can begin to think about the magnitude of C. Remember, the magnitude is the length of the vector itself, or as shown, the hypotenuse of this right triangle I've made out of the vector and its components. So this is kind of the mathematical statement of that, but it's simply taking the magnitude of the components, squaring them, adding them together, and square rooting them. Pythagorean theorem, right? Okay, so that gives us the magnitude of C. The only thing that's left to find is the direction. We're asked to report the direction as a counterclockwise angle in the typical way from the positive x-axis. So we can't do that directly, but what we can do is find a angle, or an angle. And I've labeled this interior angle here alpha, just to give it a name. And I know that inverse tangent can tell me the angle if I know the opposite and adjacent side. Well, I do know the opposite side, it's this, or the length of the x component. And I do know the adjacent side, it's this, or the length of the y component. So doing opposite of adjacent and then taking the inverse tangent, the calculator tells me that that angle alpha is 42 degrees. So am I done yet? Not quite, because remember we're trying to figure out what it is in the counterclockwise direction. So starting out in this positive x-axis and winding backwards until we hit the vector. So this big angle is what I'm looking for. What I found is this small angle. So how do I go about doing it? Well, you have to realize a simpler relationship that from here to here is 270 degrees. So if I add 270 plus 42, then I can find the whole counterclockwise angle. And then I'm done. Here's the magnitude, here's the angle. I've mathematically defined C in one of the ways I can, by its magnitude and direction. So hopefully that helps, and if you have any questions, let me know.